All right, so today we're going to be talking about energy and equilibria. All right, so this is a longer section. It's got a lot of complicated concepts that may be a little bit harder to understand, but hopefully by the end of it, you'll understand. We'll get through it together. It won't be too painful, okay? We're going to start off by going over vocabulary like we always do, and start off with these word parts. So the first word part is equi, which means equal. This word part looks like the meaning. So equi looks like equal, right? And that's why I put it on here. So if you ever see this word equilibrium, which you're going to encounter in this section, then you should think equal, right? It looks like equal. It does mean equal. So equilibrium means balance. So really what it means is when opposite forces are in equal balance. So we see this often in systems. We use it when talking about systems. Often it means maybe one part of the system is not much higher than another, or that maybe over time the system doesn't change too much, it stays the same. There's another word we're going to encounter, homeostasis. Homeo also means similar to equal, kind of like the same. And then stasis means state, right? But kind of homeostasis has a similar meaning to equilibrium, right? But we'll get there when we get there. All right, another word part we're going to go over is thermo, okay, and that means heat. You might have seen this prefix before in maybe a word like thermometer. Meter means to record, so thermometer means like an instrument to record heat, and that's what it is. In this section, we're going to be learning about thermodynamics. Dynamics means movement or change. Okay, so when we talk about the study of thermodynamics, we're talking about the study of heat change. Okay, and then finally we have inter, which means between, right? So the example we have here is interrelationship. So we know the word relationship. You can guess the meaning, right? The relationship between two or more different things, right? We also see this word. We see this word all the time, or this prefix, excuse me. Like for example, the internet. It's a connection, the net, a network of different computers, and they're all connected. So it's a network between different computers. All right. We're going to keep going on here. I'm going to go through this quickly because we're going to review it as well later with maybe pictures and things like that. It'll make more sense later. So I'll just go through it quickly. This is just for your own studying reference if you want to look up important words for the chapter. First one is resilience. It's the ability of a system to bounce back after a disturbance. Okay? And then we also have tipping point, which is when a system is pushed past the point of returning to its original state. And then we have positive feedback, a process that destabilizes the system. It gets pushed into a new state of equilibrium, right? And then we have negative feedback. It's a process that stabilizes a system after a disturbance. Okay, so a lot of these words are related, and they connect to each other, and we'll discuss later in more depth how they are related and how they work. To start off, we're going to talk about ecosystems. These again, just talk about word parts. Eco is something we've seen before. Eco means environment. System is the word we know. It's shitong, right? So an ecosystem is a community of living and non-living things that work together. Okay? There is no particular size to an ecosystem, right? So a small pond can be an ecosystem, or Jiangsu province can be an ecosystem, right? That it could be very big, it could be very small. A desert is an ecosystem. A tree is an ecosystem, right? It is not defined by its size. It's defined by living things and non-living things working together. So in a pond, it's the water, it's the minerals, it's the fish, It's the bacteria, the algae, all working together. Um, and yeah, that's what defines an ecosystem. Uh, Additionally, they involve interrelationships, there's that word, among climate, geology, soil, vegetation, and animals. If you don't know what this word geology means, geo means, oh, like rock, right? So the study of rocks. So it's we're talking maybe in an ecosystem you're going to have uh, this whole geology that is also important to understand. And then again, also the plants and the animals and the soil. It's everything, right? So they are linked together by transfers and transformations of energy and or matter. Okay, so nothing is in isolation, right? Um, they're all these systems are open. So in an ecosystem, plants interact with animals. Plants interact with the soil and with the sun, and they transfer energy and transform energy, right? And there's this transfer and transformation of energy and matter. So that's part of the definition as well. Now, if we look in this picture on the right, we see kind of three terms. They are similar but different. Okay, so ecosystem, again, it's this interplay or interrelationship between living and non-living things. We also have here habitat. So habitat, you can think of the word habitat as like home. Okay, it's the home for an animal or a bug or whatever, right? So in this case, a tree can be both an ecosystem and a habitat, right? It's an ecosystem that has bugs and again decomposers, birds, obviously, vegetation maybe growing on it. If you have these the mosses or funguses growing on it. So it's an ecosystem. It's an interrelation between living things, but also non-living things. Obviously, the bark, the climate, etc. But it's also a home for all these different things, right? It's a home for the fungus. It's a home for the bird. It's a home for the bugs. So it can be both, right? So typically, just when you think of habitat as home. It's home for an animal or home for a living thing. A plant community is a community of plants, right? It really is pretty simple. It's just it doesn't have to do with its interrelation with animals. It's just how plants interact with each other, right? It's how they are together. So, all right, let's keep going. Let's talk about equilibrium and feedback loops. So here's that again. We're already getting into the definitions. Let's start off. Let's talk about static equilibrium. So in this system state, there is no change over time, right? So we see this picture from the beginning. Doesn't matter what the time is. It could be 1 hour, it could be 1 day, it could be 1 year. There's no change at all. This is static. That's what static means. No, kind of like no change. It cannot occur in a living system, right? They're too dynamic, right? Now, this can happen in a living system. Steady state equilibrium. It's similar but different. You'll notice they both have this word equilibrium here. Well, the difference is when in a steady state equilibrium, there is some change. It goes up, it goes down, but in the average, it stays the same. Okay? So an example of that would be like your temperature, right? Over time, you get a little bit hotter or a little bit colder, but over the course of your whole life, it's always about the same. It never changes too much. And that's because your body, when you get too hot, you sweat. When you get too cold, you shiver. Or you drink hot tea or whatever you do, right? But overall, it stays about the same, okay? And the official definition, status of open systems will not change in the long term, but it may change in the short term. So that is the difference. Static equilibrium, no change at all. Steady state equilibrium, there is change in the short term, but in the long term, it stays the same. Okay? Now, here's another example. This time with biomass, right? So in a forest ecosystem, we might see growth of trees at the beginning, but then there might be, disease that affects those trees, and we see the amount of trees goes down. Well, you see it recovers after that disturbance, and then you have a fire, it goes down. Then it recovers in numbers over time. But overall, the health of the forest stays about the same. It's in a steady state equilibrium. That's a good thing. We want it to stay about the same. We want these ecosystems to not change too much, right? And then here's this question. If a forest was partially destroyed, would it grow back? Okay, and the answer is it depends. Okay, it depends on a few different things. Now, it's related to this topic, stable and unstable equilibrium. So if the forest is in a stable equilibrium, again, equilibrium means it's an equal balance, then that means that over time, if there is a disturbance like a fire or a disease, it will lose numbers, but it'll eventually come back in numbers. Maybe it's a healthy forest and it has resilience, and it will return to its original state, okay? Its original equilibrium. So we consider that a stable equilibrium. Now, not all forests are as healthy, right? They're not as resilient, right? And we might consider those in an unstable equilibrium, right? So after a disturbance, if the forest has a disease, or like the trees have a disease, or there's a fire, or humans come and chop down the trees, it never recovers, okay? And that's not ideal. That's not what we're hoping for. So if they do not return to their same equilibrium after a disturbance, they are described as unstable. And there are a number of possible reasons why this might happen. It depends on the factor, but typically the more healthy an ecosystem is, the more stable it is, right? So typically if we see a disturbance cause a change in equilibrium, it's typically a sign that something was wrong to begin with. Okay, and here's this word we talked about at the beginning, homeostasis. Okay, again, homeo is kind of like the same state, the property of a system to maintain a stable, constant condition. Okay. Now let's talk about positive and negative feedback. So these are also words we saw at the beginning, but now we'll have some examples. So negative feedback, a process that stabilizes a system after a disturbance. Stabilize, winding, if I remember correctly, right? The system gets better or goes back to normal, right? So in this example here, we have predator and prey, right? So let's say we're in an area where there's lots of rabbits, there's abundant prey, that can support many predators. Well, if there's now many predators that are born, what happens to the prey? Well, they get eaten. That depletes the prey population, so now there's few prey. Well, if there's few prey, what happens? There can only be a few predators. When there's few predators, that allows the population of rabbits to grow. What ends up happening is the population numbers go up, they go down, they go up, they go down, but it's stable over the long term. It returns back to normal. So Negative feedback is really a good thing because it's stabilizing for a system. Okay, it's when we have positive feedback that we have issues. Positive feedback is destabilizing. So that means it's not stabilizing. It's causing it to not be stable. So a process that destabilizes the system, it gets pushed into a new state of equilibrium, and the situation gets worse. So the example we have here is one that maybe we are familiar with. It's climate change, right? Unfortunately, is a positive feedback system, and the problem, as the problem gets worse, it gets worse and worse and worse and worse, and that is an issue, right? So that's why scientists, try to warn people about this. So it starts out over here, climate warming acceleration, which causes thaw ponds to be formed, which causes erosion and liberation of organic matter and nutrients, which causes microbial activity, which causes more greenhouse gases, which causes the climate to warm. So you kind of are thawing these ice stores, right? Which is going to release these microbes and which is going to cause more greenhouse gases, which is going to cause more climate change. And that just gets worse and worse and worse and worse. There's nothing really there to stabilize it except for, maybe humans intervening. Ooh, I thought I took this out. Well, no, I guess that makes sense. So yeah, it's basically, what are some positive and negative feedback systems that you can think of? So you can think about it for a second. I already gave a few examples, right? But some, so again, for like negative feedback, we have body temperature. If you get cold, you shiver. If you get hot, you sweat. So that's a very classic negative feedback example. Additionally, the prey-predator example is another example. Positive feedback is a stampede. So if one cow starts running, that causes 3 cows to start running, which causes 7 cows to start running, which causes all the cows to start running. So you move from one equilibrium, which is cows standing around, to a new equilibrium, which is all the cows are running. And so we move from a stable condition to a unstable or destabilized position. So here's some more positive feedback examples. So negative feedback, I'll be honest, is maybe more common. It's maybe easier to think of some examples, right? But I can think of maybe my computer or things like that, like my house, my system. So when the temperature gets too hot, what happens? The air conditioner turns on. If the house gets too cold, the heater turns on. That's a negative feedback system, right? So there's many examples that are pretty easy to imagine in the world for negative feedback, but I have some examples for positive feedback because maybe it's a little bit harder to think of. It's a little bit more uncommon. So here's one. So fatigue, which is like being tired, diminishes your ability to cope with stressors in a healthy way. Your inability to cope with stressors disrupts your sleep. Disrupted sleep increases your fatigue, right? So you being tired makes you more stressed. You being more stressed makes you more fatigued. You being more fatigued makes you more stressed. And it just keeps going on, and it doesn't get better unless you change something. You change the dynamic in some way. Okay? Here's another one. Population. So this is another positive loop. As more babies are born, you have more population, which means more babies are born. That one's pretty simple to understand. It's not that simple. We'll talk about that in Unit 8. But in the big picture, that's generally true. If there's more people, there's more babies. If there's more babies, there's more people. So that is a positive feedback loop. And then again, this climate example, climate warms, you buy or use more air conditioning, which causes you to use more energy, which emits more CO2, which causes the climate to warm even further. Again, it's another positive feedback loop that we're sort of stuck in. So that would be a bad example. So here is translation into Chinese. You could pause the video and look at it if you would like to. Okay. Now, here's a significant idea. As an open system, an ecosystem will normally exist in a stable equilibrium, either in a steady state equilibrium or in one developing over time. For example, succession. So we haven't gone over succession yet, but we will in future units. It's basically kind of the development of a forest over time. Okay. And it's maintained by stabilizing negative feedback loops. So this is many of these ideas we've had already put together. So we know what open system is. We know what an ecosystem is. We know what stable equilibrium is, steady state equilibrium. We know what a stabilizing negative feedback loop is. So now we can understand most ecosystems are in a negative stable feedback loop, and as a result, they stay in a steady state equilibrium, okay, which is a stable equilibrium. So most ecosystems will normally be in that situation. Now, the opposite, positive feedback loops, which are destabilizing, will tend to amplify or grow changes and drive the system towards a tipping point where a new equilibrium is adopted. So, let's I'll try. We'll see if we can get to an example in a second, right? I can't think of one off the top of my head. But to start, we need to define what a tipping point is, because that's a new vocabulary word, right? So I want you to think just to yourself, how would you react if a stranger flicked your ear once? So that's flicking, is to do that motion. If they flicked your ear once, how would you react? Maybe you get angry, or maybe you would look around confused, like, why? Who is that? Is that my friend? Why did this person flick my ear? You'd be more confused than angry, right? Now, if a stranger flicked your ear many times, kept flicking you, would you still be confused? Maybe. But would you be angry? Now, there's a good chance if someone keeps doing it and they're a stranger, you might start getting angry. So the idea here is that is what we call a tipping point, the point where you get angry, right? And resilience is your ability to be patient, right? So resilience is the ability of a system to bounce back after a disturbance. So for example, let's go to the temperature example. If I get too hot, my body is very good at cooling me down by sweating and maybe telling me to go get water, right? So your body is actually a very resilient system to heat, right? So it has high resilience. It's able to bounce back after disturbance. It's able to be resilient, right? If you are low resilience, the system does not return to its original state. But generally, being high resilience is a good thing. To bring back the example we had earlier, a forest returning to normal after a fire is maybe a sign of high resilience. If the forest does not return to its original state, we might consider that maybe low resilience, right? In this example, if a person flicks your ear 3 times and you turn around and you get angry, you punch them, maybe it's low resilience, right? Your patience got smaller and smaller very quickly, and you reached a tipping point where you got angry, you punched the person. If they flick you 20 times and you do nothing, you stay patient, we might consider that high resilience. But typically, there's a point where everybody reaches a tipping point, right? If that person started slapping you, then you might get angrier much quicker. So it depends on the situation, depends on the disturbance, the strength of the disturbance, depends on how resilient you are or how resilient the ecosystem is, right? So these are just, these are two terms that are very related, okay? The more resilient system is, the better able it is to keep from going to the tipping point. The less resilient it is, the more likely it is to hit the tipping point. So another example, again, is maybe temperature in your body. Your body's able to keep the temperature, but at a certain point, you will reach a tipping point where you're too hot. It's just your body can no longer cool you down anymore, and you get a fever, and then you get dizzy, and then you faint, and then possibly you can die. So that point, your body keeps you cool, and then it reaches a tipping point where it can no longer do anything more. You get ill and bad things happen. That's the tipping point, that point. So the more resilience means the better the system's working, right? So here are some pictures to show this. So at a certain point, we see this bottom picture. You push a rock up the hill, you reach the top. That top is what we consider the tipping point. The tipping point where you push the rock over, and all of a sudden things change very rapidly. Things change quickly, right? And again, it's when a system is pushed past the point of returning to its original state. Once the tipping point is reached, there's a quick change to the system. The changes are long-lasting and difficult to reverse. There is a time lag between the events driving the change and the evidence of the impact. The more resilient, the longer the time lag. Okay? We'll come back to that, but that's an important point to make as well. And the delays involved in feedback loops make it difficult to predict tipping points and add to the complexity of modeling systems. So it's hard to predict when an ecosystem is reaching the tipping point because we have these time lags, right? So the system is doing as much as it can to be resilient, and often the effects won't be shown until it reaches that tipping point, and then things will happen very quickly. So it's very hard to predict, and that time lag between when the disturbance happens or when the change starts happening and when the effects start showing make it very hard for scientists to predict when the tipping point will be reached. So an example of this might be climate change, right? So what might be happening is the Earth is trying to survive climate change, the world getting hotter and hotter, but there might be a time, and it's hard to predict, where suddenly rapid change happens, and scientists have a hard time predicting that. So it could be that 1 year there is no Beijing, there is no North Pole, where all of a sudden just everything melts, all the ice melts, and it just happens very quickly, and we weren't expecting it. And then water levels rise very quickly, and then we have these terrible natural disasters as a result. And it goes from relatively normal or slowly getting worse to all of a sudden very quickly getting worse. And that's a danger. We in trying to craft environmental policy, it's hard to predict when these tipping points will be reached. So it's best to be proactive, to try to prevent it early, just in case that tipping point is coming soon. And we see in this picture here, we have the system state moves from one equilibrium, it reaches the tipping point, and it goes into a new equilibrium, right? So the example I had with the stampede, right? Cows, very calm, stable. All of a sudden, one starts running, and then 3, and then 7. The system state starts going up, and all of a sudden, we're all frightened, and they're all running, and they won't stop running. And that's a bad thing. We need to enter a new equilibrium where cows are now running, right? Ecosystem resilience. Many factors will affect how resilient an ecosystem may be, including biodiversity. So maybe you know this word diversity, right? This is maybe kind of like difference in a sense. And we learned earlier in an earlier section, bio, which means life. So this is life diversity, right? Different types of life in an ecosystem. So that's generally a good thing for an ecosystem. And we'll talk about that a lot. In fact, we'll spend most of a unit talking about it in the future. So biodiversity is broken into 3 parts that we'll cover in this class. One is genetic diversity. Genetic means like gene, DNA, right? So within a species, there's going to be genetic diversity within that species. Habitat diversity, again, habitat is like home, right? So is there a lot of different habitats within this ecosystem? Different types of habitats. The more types of habitats there are, probably the better for animals. If one goes away, is actually typically pretty bad for biodiversity, right? So the more habitats there are and the more types of habitats there are, the more biodiversity there is. And then species diversity. They all play a part in resilience of an ecosystem. The higher the biodiversity, the more resilience. And we will talk more about this in the future, biodiversity. We'll go into it more in depth. But just know that for now, it's very important for ecosystem resilience. The more biodiversity there is, the more resilient your ecosystem is. So here's an example. So just looking at these 3 ecosystems here, which ecosystem is stronger and more likely to survive, right? The one with higher diversity, the one with medium diversity, or the one with low diversity. It probably doesn't take a lot of time to analyze to realize that the high diversity ecosystem is stronger and more likely to survive after disturbance, because let's say there's a disease that kills this type of plant, right? In this ecosystem with low diversity, that's disastrous, right? It's very important for maintaining this whole system, right? Now, these animals have nothing to eat, they die, which means this apex predator will also die. So the ecosystem will probably collapse. So its low diversity will cause it to collapse quicker, right? Same thing here with this medium diversity or medium diversity situation, right? Now, if this grass goes away, there's still food for this higher level of herbivores, right? But what happens if the apex predator, the carnivore, disappears? Okay, well, you can imagine the number of herbivores will increase, which means another number of plants or photosynthesizers will decrease, right? Which would cause this whole ecosystem to go out of balance, out of equilibrium. So it's better able to handle a disturbance than the low diversity ecosystem, but it still has some weak links, whereas this high diversity ecosystem it could lose many type of plants. If many plants go extinct, if the blueberry, this grass, the strawberry, they all go away, well, there's still plenty of food for the herbivores. Decomposers will still be okay. So, and if they lose one of the two carnivores to disease, the ecosystem can still survive. So more biodiversity is good for the ecosystem. And that's kind of the point I wanted to make here. Ecosystem resilience, let's continue on. Many factors affect, such as the storages of a system. So we talked about the storages previously. So this, some examples would include biomass. Again, bio means life, mass, kind of like the substance, matter, right? So the biomass, soil nutrients, water, carbon, and organic matter, they provide the necessary resources for ecosystems to maintain functions during and after disturbances. The bigger the storages, the better the resilience. So if a disturbance happens and it affects the water supply or the amount of carbon, then just like having more biodiversity, having more storages is better, right? It can handle a disturbance better. If there's a fire that affects the ecosystem, having more storages would be better for it to bounce back. Other factors include the size of the ecosystem. So bigger ecosystems typically mean more biodiversity and bigger storages. Climate. So some climates foster biodiversity better. So for example, tropical climates, right? There's lots of sunlight, there's lots of rain. Typically it fosters more biodiversity, whereas up in the North Pole, when we get into like taiga type of biomes, we'll talk about that later, it's not as biodiverse, which typically means it's not as resilient. Additionally, faster reproductive rates. We haven't talked about this yet, we'll talk about it later, but our strategists can recover better after a disturbance. So our strategists are animals that reproduce quickly. Think of a rabbit. A rabbit reproduces very quickly. If the number of rabbits goes down, they can quickly recover their numbers. But if a human, if we lose a lot of our numbers, well, we only have one child in our life, or 1 to 10, let's say. Depends on where we live. If we're in China, it's probably 1 to 2, right? So we don't bounce back as quickly, right? Whereas other animals might do better. Human behavior also impacts ecosystem resilience. So deforestation, cutting down trees, pollution, urban development, which means creating cities. These can all impact storages and biodiversity in an area, and that's pretty obvious. So human behavior impacts ecosystem resilience because it affects storages and biodiversity. We're not going to watch this, but this is an example of tipping point, right? This coral reef tipping point. So coral reefs in the ocean, they try to stay resilient, but there is a point of heat when the water gets too hot, where the coral gets bleached and dies. It all happens very quickly. So as the temperature rises and the system state changes, it changes from its normal equilibrium or its original equilibrium. Then it hits a certain temperature where all of a sudden it drastically changes and it becomes dead, right? The ecosystem dies off, it collapses, and now this new ecosystem where everything is bleached, which is not good. So that's an example of a tipping point where maybe scientists have a hard time predicting it and we don't see the effects until it happens. That's the danger. Okay. Climate as well, we see these interconnected tipping points. So as one gets worse, then another will get worse, on and on and on. They're all connected and it all makes everything worse. And that's worrying, right? So again, you can pause it, you can read it if you want. We're not going to go over it too much here. So let's talk more about ecosystems and feedback loops. So now we're getting into the conversation about energy and matter, which is also important for this section. So there are two basic processes that occur in ecosystems. One is the cycling of matter. So there's only a limited amount of nutrients that exist on Earth, so they must be recycled. Okay, so that's where we get things like the nitrogen cycle and the carbon cycle, blah, 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 right? It gets recycled. It goes into the soil. It goes into the air. Plants use it. Animals use it, etc., right? So it must be recycled. And then we also need to talk about the flow of energy. So all energy originates from the sun. So it comes from the sun, and it's used by plants in photosynthesis and converted to a form usable by all other organisms. So, yeah, I think you know this already, but the sun is so very, very, very important, right? It supplies all the energy for all these systems. It starts the cycling of matter, and it also creates this flow of energy. It kind of starts with photosynthesis, and then it transfers form in one way or another, in many different ways. But all energy on Earth, more or less, not all, but most, almost all, comes from the sun, right? So to go more into this flow of energy, the vast majority of energy on Earth comes from the sun as radiant energy. So we see this in this picture. That's radiant energy. That's the name for it. This energy is converted into chemical energy through photosynthesis. So now it transforms. That's the word we learned in the previous section. Transforms. It changes form, and now has become chemical energy through photosynthesis. So now it's stored chemical energy in these plants, right? This energy is then transferred through the food chain and drives the cycling of matter. So these herbivores eat plants, they transfer the energy to the rabbit, and then this fox will eat these herbivores, this rabbit, and then transfer the energy that way, right? Eventually, the energy returns to space through heat, or what's known as infrared energy. Okay? So, in every stage of the process, in every transfer, you're going to see respiration and energy returning as heat. So, animals, like us, like humans, we are constantly releasing heat from our body. So as I'm breathing, you can feel it. There's heat coming out, right? Additionally, just on our skin, things touching our skin, that's transferring energy. But for the most part, it's respiration, breathing out heat. It's also coming out from your ears, from your nose. You are releasing heat all the time, and so are animals, okay? So are plants, actually. Nope, I thought I removed that as, oh no, I keep forgetting. There's use for this, sorry. So I'm going to show you 3 different pictures, okay? And I want you to think whether this machine I show you can create energy and whether this machine I show you can run forever. Okay, so this first picture, do you think that this machine can create energy? And the second question, do you think this machine can run forever? Okay, I want you to think about it for a second. Pause the video if you need to. Okay, so that's the first example. Here's the second example. Do you think this machine can create energy? And do you think this machine can run forever? Again, pause the video if you'd like. And then this third machine here, using magnets. Okay, do you think this machine can create energy, and can it run forever? Think about it, and then we'll go over the answer in a second. So the answer to both questions is no for all three pictures. The first question is no because of the first law of thermodynamics. Okay. The second question is no because of the second law of thermodynamics. So it cannot create energy because the first law. It cannot run forever because of the second law, which is a little bit more of a complicated topic, but hopefully it'll make sense, right? So we saw this vocabulary word at the beginning: thermo, heat, dynamics, change, right, or movement. So this is study of heat change. And another way of putting it, the study of energy transformations and energy transfers that occur within and between systems. So we see on the right here different types of energy, right? We have energy from the sun, solar radiation, chemical energy, electricity, kinetic energy, sound energy, light energy, heat energy. They can transform and transfer, right, between systems and within systems, right? So this is what the study is about, and what happens when these transformations and transfers occur, and how efficiently do these things happen. Okay, so this is where we start learning about the first and second law of thermodynamics. We're going to try to keep the first law of thermodynamics simple. We're not going to try to overcomplicate things, because this is not a physics course. This is ESS, right? We don't need to go into the weeds on it, but you've probably heard of it before, and you probably understand it on some level. It's the principle of conservation of energy. Energy in a system can be transformed, but not created nor destroyed. So it can be changed, or it can be transferred, but it cannot be created nor destroyed. So what that means is all the energy that exists in the universe now is what was here at the beginning of the universe, and it's what will be here at the end of the universe. So no energy will be created, no energy will be destroyed. It just changes, right, from one form to another. And that's true of matter as well. But again, we're going to focus more on energy for this course. But we cannot create or destroy energy within a system. That's kind of a simple definition of it. And again, we're trying to keep the first law as simple as possible. But basically what this means is we can add energy to a system, we can remove energy to a system, or remove energy from a system, or change energy within a system. So when we add energy to a system, think of it like you put a pot on a stove, right? You're adding heat to that pot. You're warming up the water. You're adding heat and energy to that water. You're adding energy to that system. Additionally, when you remove energy from a system, you can remove that pot from the stove, put it onto the counter, onto a table, and slowly it will lose heat. It will lose energy. Just kind of transferring that heat through the pot into the table and into the surrounding air, etc. You remove heat from the system. Typically, I mean, really always, because systems are connected, when you add energy to a system, you're also removing energy from another system, and vice versa, right? Because these are connected. So when I add heat to the stove, when I add heat to the pot, I am taking energy from my stove, from the electricity, right? So it's transferring that energy from one system to another. We're adding it to the pot, but we're removing it from the electrical system, right? So that is an important distinction. No energy was created in this. We did it when we turned on the stove. Energy was not being created. It was just being transferred from electricity into our stove and then into the pot, right? And then eventually it will become heat, evaporate, and go into the air, really, or go into counter. It's transferring from one system to another, essentially. So again, we're going to try to keep the first, because I think it's pretty easy to understand. The basic idea is energy cannot be created or destroyed, right? So that's what you have to remember. Now the second law is where it gets a little bit more complicated. There's going to be a more complicated definition, and there's going to be a more simple definition for the second law of thermodynamics, because maybe the second law of thermodynamics is very important for science, for physics, for chemistry, for biology, for everything, right? The second law affects all types of sciences. But for our course, we're only going to be focusing on a very narrow portion of the second law of thermodynamics. We're not going to focus on some of the other parts, which might hopefully make it a lot simpler for you. So we're going to start out with a more complicated definition, because this is probably what you've learned in your class. And this is probably, maybe if you're confused, you might be confused because of this, right? So the definition: in an isolated system, the total amount of entropy will tend to increase. So again, we've learned what an isolated system is, right? It's where matter and energy cannot transfer, right? It's all stuck within that system. It cannot leave. Well, in that system, entropy or disorder will increase. Okay, so let me try to explain what that means. So we see here, imagine these are gas molecules, right? Over here, let's say we turn on, let's say we have a gas canister, a gas can in the corner. We open it up. We release these molecules into this room. What's going to happen? Is it all going to stay in that corner? No, it's going to spread out. And we kind of know this. These molecules like to spread out and become more disordered over time. Okay, so we start out on this to the right, and then over time it becomes like this environment to the left. And another way of thinking about this is this example. If you tossed bricks off a truck, which kind of pile of bricks would you more likely produce? So if I threw a bunch of bricks off of a car or a truck, what's more likely to occur? Well, it's more likely that the right is going to happen. Disorder is more probable than order. It would be very unusual for it to land like it is on the left. And that's, with matter, this is the case, right? With matter, things get more disordered. So when you hear entropy discussed, you typically hear it with this word disorder. And that's what this is talking about. It's talking about over time, molecules spread out and matter becomes more disordered over time. It tends in that direction, right? Now, here's where it might get a little tricky, but I hope you follow along with me. Okay, the second law of thermodynamics has actually two parts to it. Okay, one concerning matter and one concerning energy. Okay, they are related to each other. Matter and energy are interconnected, but they're not exactly the same. They're properties of each other, but they're not exactly the same. So matter tends to become more disordered. The word we use is disordered over time. Okay? Now, energy tends to become more spread out over time. And these are different ideas, but they are both true within this second law of thermodynamics. So we are not going to focus too much on the matter portion of the second law of thermodynamics. That's maybe for physics class or something else, right? You're not in a physics class, you're in ESS, and we're focused on energy. Energy is very important for our understanding for food chains and things like that. So we're really going to focus on that. So instead of thinking of it in the sense of disorder, you always hear that word disorder, and that might be very confusing. How does that relate to ESS? You can ignore that. Okay, so let's move on. Let me try to explain what I mean by that. So this is a simplified explanation of entropy. Over time, energy tends to disperse, okay, making it less concentrated and thus less available for use. Okay, so what does this mean? Okay, there are energy when it is tightly together, like on the left. It's maybe not the correct term, but we're going to use it just for simplified, so you can understand. It's usable or workable, right? The more tightly concentrated energy is, the more usable it is. The more spread out it is, the less usable it is. Okay? So, what this second law of thermodynamics is saying is that energy over time will start out more like the left and then spread out and become like the right. It goes from a workable and usable state to an unusable state. Okay? This, when we use energy in our house, we typically are using this concentrated type of energy, right? And then after we use it, it becomes heat. It spreads out, and then it's unusable. We can't really use heat. Heat is an unusable type of energy, or it's a very inefficient type of energy, whereas other things like electricity, things like that, or chemical energy that we get from food is more usable, right? We can use it for energy. Okay. So again, the first part of entropy, over time, energy tends to disperse, making it less concentrated and thus less available for use. Simultaneously, matter tends to become less structured and more disordered. Entropy has to do with both energy and matter, but in this course we will focus only on energy, or mostly focus on energy. Okay? And so that's why I struck out this line about matter. Okay, you can ignore that for the most part. The main point you need to know is that energy spreads out. The main way this happens is it becomes heat. At least for this course. Or the main way that this happens is heat. When it's concentrated, we can use it. When it is heat, we cannot use it. Okay, so let's keep going. Another way of thinking about this, again, you maybe this will help you understand it a little bit better. At the beginning of the universe, at the Big Bang, all energy and all matter was concentrated together in a very small space. And then, at the end of the universe, what's going to happen? Everything's going to be spread apart. This is called the heat death of the universe. Energy and matter are expected to spread out, and everything will be so far apart and so disordered that the universe will die. That's the heat death of the universe. Okay, so this is what kind of this second law of thermodynamics is showing. At the beginning, it started off very, very concentrated. At the end, it will be very, very spread out and disordered, right? But we're just kind of in the middle, right? There's some order, there's some concentrated energy, and we can capture it. We can capture the order, but over time, it tends to become disordered. So here's some more examples about energy. So again, for this course, entropy can be seen as the spread of energy in a system. When energy has spread out, it is said to be higher entropy. So again, when energy is concentrated together, it is low entropy. Okay, it's concentrated. When it is spread out, it is higher entropy. Okay, and the tendency, the natural tendency of energy is to spread out and become higher entropy. Okay. Now, we can see these are some real world examples of this in action. So on the left, we have examples of concentrated energy. You know, I'm being very loose. These are not, I think maybe some scientists might be rolling their eyes here at me for some of the terms I'm using, but this is a general, I'm just trying to make you understand the concept, right? So I'm using very simplified language, but these are concentrated examples or examples of concentrated energy. This concentrated energy doesn't last forever, okay? So on the left, we have gas, right? We have, so gas came from the ground over millions of years, right? We have electricity, we have this chemical energy in the form of plants. Here we have some hot pot, right? We can eat it. And then what happens? They get consumed and used. Okay, so these were fuel. These four on the left, they're like fuel, they're concentrated energy, they are available to be used. And then when they're used, what happens? This concentrated energy spreads out and it becomes heat. Okay, so when we use this fuel in our car, what happens? Well, we see here what part of the car is getting hot? Well, the engine. The engine is getting very hot. It's in use, right? Additionally, this computer, when we use electricity from the wall, well, your computer gets hot from use over time. So usage creates heat. That heat leaves the computer. That's why your computer cannot run forever. If you unplug it from the wall, it will eventually die, right? It needs a constant stream of energy in the form of electricity. Same thing with us, right? We need energy too. Humans need energy. We eat hot pot. And then what happens? Well, you can see in this picture, our skin is very hot and our breath is very hot and it comes out of our ears. We're constantly losing heat into the environment. Okay, so yes, we do need to eat constantly because to use as fuel, because if we don't, eventually we will lose this heat and we will die, right? That's the reason. And then same thing with animals, in this case a rabbit. They eat plants. They use it, and you see where is the heat escaping? Well, it's escaping through the ears. They have fur, so it's kind of more insulated, that keeps the heat in. It's trying to keep the heat in, but it escapes through the ears. It escapes through the nose, through the eyes. It will escape at some point, right? So it starts out concentrated, usable. It is used, and then it spreads out as heat, and it's no longer usable. We cannot use heat for energy, or at least not very efficiently. That's why we don't try, very often. Okay, so this is what you need to understand for this course. This is why this topic is very important, because this is important for understanding food chains. Because again, like this rabbit eats these plants. They get energy from the plants. Where do the plants get their energy from? Well, they get it from the sun. And then maybe another animal will eat the rabbit. There's a food chain, right? This dispersal of heat is actually very important for understanding how food chains work, why they're fragile, and all these different things. So again, the sun, fortunately for us, is the source of all these concentrated energy sources. We're very lucky, because actually when we use all these concentrated energy sources, it's very inefficient. We don't use it very well. It very quickly becomes heat. But fortunately, we get a constant stream of energy from the sun, which provides all the energy that we need. And that's very fortunate for us. Okay. So let's keep going on. Hopefully this makes sense thus far. An increase in entropy leads to a reduction in energy. So you go back to this. The more spread out the energy is, the higher the energy is. Okay? These on the right is the same as this picture on the right. Okay? This on the left, where it's more concentrated, is more like these on the left. So as we move from the left to the right, we move from more concentrated to more spread out. From low entropy to high entropy. Okay? An increase in that entropy leads to a reduction in energy. So as we go from this to this, we lose energy as a result. So each step along the food chain, each successive step, we're losing energy along the way. And that's very important to understand. And that's why we learned this, by the way. Energy conversions are not 100% efficient. Energy is lost to the environment in the form of heat. So really, when we looked at these pictures at the beginning, the main reason why these will not run forever is because they will lose energy due to heat. Okay? Yes, they seem very clever and they will cycle back and forth, but over time, heat will be created, heat will get lost to the environment, and energy will be lost over time. Okay? So that's why these type of machine, if you ever see any machine online that claims that energy is being created or that an energy can last forever, it's impossible. It is completely false. This is a japian, right? This is a scam. Okay? Sorry, here's the Chinese, so you can pause it and look at it. Okay? Now, what this looks in real terms, again, here's an example of a food chain. And we can see how inefficient and how quickly we lose energy. Okay, so this whole when we say as energy spreads, you lose as you go. How am I explaining this? So as entropy increases, we lose more and more energy. So each step, as energy spreads out, we're losing more and more to heat into the atmosphere. So let me explain what I mean. I might be losing you. So we start out with 1,000 joules of light energy. Joule is a form, a measurement of energy, right? So we get 1,000 joules of light energy. This goes into this plant, which photosynthesizes that energy and produces 10 joules of energy available as food. 990 joules is energy lost to the environment. So the 990 of 1,000 is already lost to the environment. It's very inefficient, okay? But it was able to get 10 joules of energy. It was able to capture some of it and use some of it. So now this plant exists. It's eaten by a herbivore, and 1 joule of energy is now available to this herbivore, and 9 joules is lost to the environment. Again, as the energy spreads out, we are losing energy, right? So the natural, as energy becomes heat that gets lost to the environment, we are losing energy each step of the way. That 1 joule gets sent over to this lion. The lion, or the carnivore, will get 0.1 joule of energy from this herbivore, okay? And 0.9 will be lost to the environment. So as we go higher and higher up the food chain, we started with 1,000, it went to 10, then 1, then 0.1. We lost 999.9 joules of energy in the process, lost as heat. And you might be wondering, how is this possible? Well, it's possible because there's a lot of energy from the sun. So the sun keeps giving energy. It never stops giving energy. So there's going to be lots of plants. So this animal can eat lots of plants and get energy that way. And then this animal can eat the herbivore and get energy that way. The sun is the source. But along the process, we lose so much energy that really it's very inefficient. It's not that's why food chains are rarely longer than 5 steps long, right? So you might ask yourself, why isn't there an animal bigger than a lion that eats the lion? Well, the reason is there's not enough lions. There's not enough energy available. So there's in an ecosystem, there might be 100 lions, right, in total, in a big area, right, in kind of somewhere in sub-Saharan Africa, you might see 100 lions in an area. Well, that's not enough energy to sustain another level of the food chain. So that's why they are the top, the apex predator. There cannot be bigger because there's not enough energy to sustain another level. So food chains, in a sense, are inefficient. They lose most of their energy to heat. And that's a big point to understand here. Let's talk about it a little more. So as energy passes through a food chain, some of it is passed on, but most of it is lost as heat. With each energy transfer, more and more heat loss occurs. So each step, more and more energy is lost as heat. Energy starts out from the sun. Solar energy, which is highly concentrated and ordered, is considered low entropy, as it is used by organisms, converted into chemical energy through photosynthesis here, and then passed through the food chain here and here. It becomes more dispersed as heat and becomes more and more high entropy, particularly due to respiration and other biological processes. So you breathe out and you use the energy, and that causes the heat to get lost to the environment. Respiration means kind of to breathe out. Okay. Here it is in Chinese. Oh, too far. Okay, so you can pause it, read it if you'd like to, right? And again, how does this relate to ESS? So the main takeaway for ESS, why is this important? Like I said, food chains are inefficient due to the second law of thermodynamics. They lose most of the energy as you go each step up the food chain. You lose more and more energy as heat. Okay? Less and less energy is available as you move up the food chain. Okay? As a result, there is more biomass at lower levels of the food chain since less energy makes it to the top. So before I move to the last point, this is what I mean by that. So biomass, again, bio, life, mass, like matter. You can think of it like weight. Okay, so these plants at the bottom, there's a lot of plants. Okay, and as you go up each step of the food chain, there's less biomass available. And eventually, there's only a few apex predators because there's just not enough energy to sustain them. So like in a forest, right, there may be only 100 bears, or there may be only 100 wolves in an area, just because there's not an unlimited amount of food, right? It doesn't make its way up to the top. So there's less and less biomass as you move up each level of the food chain because there's less and less energy transferring up. And thus, these animals at the top can't be supported. Okay? So that's what that means. That's why, that's the effect of the second law of thermodynamics on the food chain. Okay? The second law of thermodynamics also explains the inefficiency and decrease in available energy for energy generation systems. We'll probably talk about this future units, right? So things like power generation systems, right? They don't run forever, right? They eventually they tend to be inefficient, and they tend to decrease in available energy over time. We're trying to solve this, but it's a tricky problem to solve, right? And that's where the second law of thermodynamics comes in. But again, we'll tackle that more in the future, but that helps explain why that's true. So that's why your battery in your phone doesn't last forever, right? As you use your phone and you use the energy, your phone gets hotter, it loses heat, it loses energy. So in the future, your batteries will be better, but there's always a limit, right? And we're trying to solve that, but they're still a little bit inefficient. So you still need to charge them. And we get that electricity initially from the sun, right? That's the origin of that electricity. And here it is in Chinese, okay? Let's talk about efficiency, okay? So efficiency can be seen by this equation here at the top. Efficiency is useful outputs over inputs, okay? And you multiply it by 100 to turn it into a percentage. So, in a food chain, only 10% on average is passed on to the next level of the food chain, okay? This is considered inefficient. This is called the 10% rule in ecology, okay? So, at each step of the food chain, you lose, you only retain 10% of the previous trophic level, okay? So on average, it's not always true, but on average that's the case. So yeah, so you can see that in this. We'll talk about a lot of these things we talked about in this class. Again, this is an introduction unit. We talk about the 10% rule in a future class. We talk about these power generation systems in future unit in class. So we'll get there, right? This is just introducing you to it. We're gonna skip that, and then we'll talk about sustainability, next. All right.